Hello, everyone. I will introduce a new method for solving crystal structures. The initial study of this method was published in this paper. Today, I will focus on the main ideas. For details like the mathematical formulas, please refer to this paper. When X-ray passes through a crystal, it deflects into many spots. Each spot is indexed by three integers h, k, l. The intensity of the spot is measured. The intensities at all deflection spots make up a raw data set. To solve out the structure, we use a concept called the stretch factor. A stretch factor describes how X-ray deflects into a deflection spot. It is a complex number. That means it has both amplitude and phase angle. The amplitude equals the square root of the measured intensity. However, the phase angle is not directly measured. This is a problem called the phase problem because in order to calculate the electron density by Fourier transform, we need both amplitude and phase angle of the stretch factor. People have already solved this phase problem by applying the dual space cycling strategy for solving crystal structures. This dual space strategy starts by making initial guess of the phase angle. Then use Fourier transform to calculate the electron density in XYZ space. After making some improvement on the electron density, the calculation goes in opposite direction. Use reverse Fourier transform to get a new estimate of phase angles in HKL space. After improving the resulting phase angles, the calculation repeats a next cycle and doing many cycles until the calculation converges. From the final electron density, we derive the atomic model. That's how usually people solve crystal structures. Even though the phase problem has already been solved, from a theoretical perspective, we may still ask, do we have to deal with this phase problem in order to solve crystal structures? Is there a way to completely avoid this phase problem? Yes, the phase problem can indeed be avoided if we solve structures by using a different strategy, using the optimization strategy. In this optimization strategy, instead of targeting the electron density, we may directly targeting the atomic model. That is, we may assign each atom to XYZ coordinate. We know how each atom scatters X-ray, and this is described by its atomic scattering factor. So once we know where the atoms are located, we can directly calculate the intensity of each scattering spot. And this calculation does not involve the phase angle. So going this route, the phase problem never exists. Now you can see we can compare the calculated and the observed scattering intensity to get the aR1 factor. And by adjusting the location of the atoms, we may minimizing the aR1 factor and found the correct locations of all atoms. This logic is simple and straightforward. But unfortunately, there is a small problem with it. No one can practically use this strategy to solve a sketch, simply because there are so many atoms in a model, and the calculation is too overwhelmed for current computing technology. Even though it is impossible to immediately determine the locations of all atoms, we have found that we may go step by step, and at each step we only determine one atom using the optimization strategy. This requires to define the single atom aR1 as aR1. The original aR1 depends on coordinates of all atoms from 1 to n. Let us consider at a particular step. We have already determined the locations of atoms from 1 to j minus 1. The locations of the remaining atoms from j to n are still undetermined. However, we only want to deal with one atom from all these undetermined atoms. Let us say we want to deal with atom j. For the rest undetermined atoms from j plus 1 to n, we do not want to deal with them at this point. So we delete all terms in the aR1 factor that are dependent on the coordinates of these atoms. The resulting approximate aR1 only depends on the unknown coordinates of atom j, because the coordinates of atoms from 1 to j minus 1 are the known parameters. So atom j can be located by minimizing the aR1. There is one point should be very careful. When deleting terms dependent on coordinates of the atoms from j plus 1 to n, we should not delete too much. The resulting aR1 no longer depends on the coordinates of these atoms, but it should still partially dependent on the atomic scattering factors of these atoms. This partial dependence on the atomic scattering factors if are also removed, the method will become much worse. Now, how to locate the very first atom? Very simple. You may put the first atom anywhere you want. For convenience, just put it at 0.3, 0.3, 0.3. In this picture, the yellow ball is the first atom, and the red dots suggests where the other undetermined atoms are located. After put the first atom, we define aR1 for the second atom. When we move the second atom around, we may imagine when it moves over a red spot where there should be an atom there, aR1 will decrease because the model will match the real situation better now. So we predict there is a local minimum at each location where there should be an atom. Obviously, we should put the second atom at the lowest local minimum point. Let us say here is the lowest local minimum point, and we put the second atom here. After determining two atoms, we can now define the aR1 for the third atoms. Again, we move the third atom around and put it at the lowest minimum point of its aR1. In this way, we determine third atom, and similarly, we determine more and more atoms until finally we complete the model. Now, with this example, we are lucky because in one run, we determined the correct model. Here is an example we are not so lucky because after one run, we see some funny atoms in the resulting model. Here I have circled these funny atoms with red lines. These are called ghost atoms, and we should delete them. Okay. After deleting these ghost atoms, the calculation can be resumed, and finally we get the correct model. Okay, so here is another example that was solved by the aR1 method. In this example, there are 424 atoms in this model. The black atoms are carbon atoms, and the red are oxygen atoms in this picture. So this model only contains light atoms. Now, this is an example also solved by aR1 method, and there are 864 atoms. Here, black are carbon, orange color are nickel, yellow are sulfur. So, in this model, there are some heavy atoms. The aR1 method can locate single atoms one by one. The idea, in fact, can be extended to deal with a fragment. In order to deal with a fragment, we need to define the partial structure R1, PR1. The definition is almost the same. Suppose we already know the coordinates of atoms from 1 to I-1. Out of the remaining undetermined atoms, the atoms from I to J belong to a fragment, like a benzene ring, whose internal structure is known. Then we delete all terms that are dependent on the rest atoms from J plus 1 to N. The resulting PR1 will only depend on the orientation and the location of the fragment. This is because the internal structure of the fragment is known. So, by minimizing PR1, we can determine the orientation and the location of the fragment. Here is an example solved by combination of aR1 and PR1. In this model, there are tin atoms and iodine atoms, and these are located one by one by the aR1 method. And then there are 4 C60 molecules. They are located and oriented by the PR1 method. Finally, this example was solved by PR1 only. In this model, there is only single C60 molecule, so we can conveniently put the cell origin at the center of the C60 molecule. The molecule is then oriented by the PR1 method. Finally, we use the PR1 method to locate and orient the two P4 molecules. Okay, Python codes are used in this work, and the Python codes can be downloaded from this GitHub link. If you have any questions about the aR1 methods and the Python codes, please contact me. Thank you all for your attention.